In our previous video, you saw the C0 gate given by this circuit, where the first qubit is the control qubit and the second qubit is the target qubit. And whenever the control qubit is 1, the NOT gate is applied to the target qubit. This operation is given by this expression and it is represented by this matrix. So this is an example of our controlled operation, and C0 is a specific case for NOT gate. We can generalize this for any unitary operator U given by the circuit here, where the control bit target bit gives us the control bit into U operating on target bit only when the control bit is 1. So these were the example of condition on a single qubit. Now let's see an example of multiple qubit conditioning. So this circuit here represents a Toffoli gate where we have two control qubits and one target qubit, and the NOT operation will only work on the target qubit if both the control qubits are 1. The truth table of Toffoli gate is given here, and if you'll see the last two entries, the target qubits are flipped from 0 to 1 and 1 to 0 only when both the controlled qubits are set to 1. Now we can generalize the multiple qubit conditioning given by the expression CNU operating on x1 x2 xn into psi, which is equal to x1 x2 xn u raised to x1 x2 xn into psi, where we have n plus k qubits input with n control bits and k target bits, and u is a k qubit unitary operator and CNU represents the controlled operation. And if you see, we have u raised to x1 x2 till xn, where x1 x2 till xn are the products of the bit x1 x2 xn, and u is applied to the last qubit k only if all the n qubits are equal to 1, otherwise nothing is done. This generalized operation can be given by the circuit where n are the number of all the control qubits and k are the number of all the target qubits that is been operated by the unitary operator u. Now let's see the implementation of CNU gate operation where U is a single qubit unitary operator. So for n controlled qubits, we have n minus 1 working qubits, all having the values 0. The control qubits are in the computational basis set C1, C2 till Cn, and we have to produce the product C1 dot C2 dot till Cn. So we have to AND C1 and C2 and the product with C3 and so on using the Toffoli gate until the final work qubit is in the state C1 dot C2 dot till Cn. Next, U is operated on the target qubit only if the final work qubit is set to 1. Finally, the last part of the circuit just reverses the steps, returning all the work qubits to their initial state 0. Let's see an example for n equal to 5 control qubits given by C phi U. This operation is represented by this circuit diagram. So first you can see that we have 4 work qubits 0000 states, such that first operation of Toffoli gate we have 0 XOR C1 C2, which will give us C1 dot C2, and for the second operation of Toffoli gate we have 0 XOR, now this is C3 and this is the result of the first operation, which is C1 C2. So this would be C1 C2 C3 XOR 0, which will give us C1 dot C2 dot C3. These are all the AND operations. Similarly, by operating the third operation, fourth operation, we'll finally have at this point C1 dot C2 dot C3 dot C4 dot C5. That is all the AND operation of our control qubits. And the unitary operator will only operate on the target qubit if the value of this state, which is our C1, C2, C3, C4, C5, is equal to 1. Otherwise, it will be left alone. And then we reverse the steps such that this state, which is our C1, C2, C3, C4, C5, is XORed with C5, and this state, which is our work qubit, having the value C1, C2, C3, C4 and C5, as you can see from here. So we'll have C1 dot C2 dot C3 dot C4 dot C5 XOR C5 into again C1 dot C2 dot C3 dot C4 dot C5. So it would be C5 dot C1 dot C2 C3 C4 and C5, and if any one of this qubit is 0, this whole state would be 0, and if not, it would be 1. Similarly, if this whole thing is 1, this whole thing would have to be 1, which implies that all the values of Ci's were 1, and 1 XOR 1 would give us 0. So we reversed our work qubit to its original state 0, and same operation is done for the third last work qubit, then for the second last work qubit and the first work qubit, and thus we have reversed the operation. So I hope you understood the controlled operations in a quantum circuit.